learn how to manipulate it and use it rather than blunt memorization. So we're going to jump right in today with our conversation on cyclohexanes. We do have a wonderful guest speaker coming up for the latter half of class today, portion of it, but we are going to still discuss our cyclohexanes today. So, as we talked about last class when we introduced cyclohexanes, the carbon to hydrogen ratio is different than an acyclic hydrocarbon species. We make these by taking our sp3 carbon pieces, push and pull until they click. If they don't click, I can pretty much guarantee your cyclohexane will fall apart today when we get to conformation changes. Take 6 of these and connect them into a cyclohexane structure. Last class, we also learned about how we can use Newman projections to communicate staggered and eclipsed. And if we look down a carbon-carbon bond, we can see if the bonds or the atoms, the substituents, are staggered as they are here, or if we rotate it and see that they are eclipsed when the front carbon bond matches the back carbon bond. So your cyclohexane rotates around carbon-carbon single bonds. It doesn't rotate as freely as an acyclic compound. It can only rotate so much. But this cyclohexane is not a crystal structure. It rotates around these carbon-carbon bonds. So it can have different conformations. We're going to start with the boat and then move to the chair, because the chair makes up about 99.9% of cyclohexane molecules. So hold carbon 1, whichever carbon you decide is carbon 1. Count 1, 2, 3, 4 to the opposite of your cyclohexane, and then bring both hands up. This is our boat conformation. This one is not as stable because we have the 2 substituents up here where my fingers are having a flagpole interaction. They have steric hindrance. They're getting in each other's space. So although the boat looks cool, and hopefully you have your boat with your cyclohexane, it is not the most stable conformation. Instead, most cyclohexanes exist in a chair conformation. So take your hands on opposite sides, bring them both up to make the chair, and then bring your left hand or right hand down, whichever one, and this makes the chair conformation. As we showed last class, this is the back of the chair, the bum of the chair, the footrest of the chair. If your chair is in a proper chair conformation, it's going to sit on exactly 3 prongs. So I'm holding this up here. You can see it has 3 down prongs that are touching my paper. If you have this on your desk, you should have exactly 3 down prongs hitting your flat desk, which means you have exactly 3 up prongs. The up and the down are called axial positions. So practice grabbing that cyclohexane, turning it into a boat, turning one down into a chair, and it should balance on exactly 3 prongs. If yours doesn't, come see me after class, because that's a really helpful strategy. So when we have our chair conformation, we want to identify the axial positions and the equatorial positions. Remember how I said it sits on 3 prongs? I'm trying to get the angle here. If you look at the side of the chair, 1, 2, 3 down prongs, 1, 2, 3 up prongs. So if I hold it like this, it sits on exactly 3 prongs. The axials go straight up. See how they're on every second carbon? Or not every second carbon. Yes, every second carbon. And the other carbons have a down axial. So up, 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 and down, down, and down. Exactly 3 on my hand. Well, then, if we have this chair conformation, again, if you've just built it now, hands on opposite carbons, up to make the boat, down with one hand, and it sits beautifully on 3 prongs. In addition to the up and the down axial, we also have these equatorial positions that are pointing straight outwards. I'm going to flip this on its side, and we're going to do a Newman projection down this carbon-carbon axis. Here we have a down, I'll go like this, down, and an equatorial, an up axial, and a down equatorial. A down axial, and up equatorial. Axial, equatorial. So we have 6 equatorial and 6 axial positions. And of course, if we overlaid these, you would see each carbon has 1 axial and 1 equatorial position. I'm going to give you 15 seconds to chat with the person beside you. If you were a large substituent, a big atom or a big group of atoms, where would you want to hang out? In the axial, one of the axial positions, or one of the equatorial regions? Go ahead and chat for like 15 seconds. And 3, 2, and 1. Hands up if you want to be in an axial position, where I have the red balls here. Hands up if you want to be in an equatorial position, one of the outsides. Agreed. Why? Who wants to just shout it out? Why? Besides, it says in your workbook that that's what's coming up. It has more space, that's right. We know that atoms and electrons like to have as much space as possible. There's a lot more room hanging out over here. You have your own like little beach area versus this flagpole interaction from these red balls in the axial positions. And indeed, that's what happens. When we have large groups, they tend to exist in a conformation that has them in an equatorial position. So if you have your cyclohexane, put red balls or your favorite color on the 3 up axial positions and the 3 down axial positions. And now you can see it hangs very nicely on 3 down prongs and has exactly 3 up prongs. Now that we've identified our axial and equatorial, did you know that we can actually make it change? Once you are holding your cyclohexane with all of the axial positions marked, watch what happens when, I'm going to go like this, I'm going to put my hands on carbon 1 and 4 again, the up of the chair where your head goes, the down of the chair where your footrest is. If I take the up triangle here and flip it down, and the down triangle here and flip it up, what happened to all of my red balls? What position are they now in? I'm going to do another flip-flop. Up and down. They're all in axial positions. Down and up. What are they in now? Now they're all in equatorial positions. Every cyclohexane has 2 different chair conformations. We can't really, I'm just going to call them chair 1 and chair 2. But we can do this flexing, and I'm going to call it a flip-flop to remind you that we need to go, the up triangle goes down, the down triangle goes up. All of the axial become equatorial, And all of the substituents that were in equatorial groups are now, all the substituents in equatorial locations are now in axial locations when we do this flip-flop. And the cool thing is both of them could exist. Well, it could go this way, all equatorial, or flip-flop, it could go to axial. And we know that carbon-carbon bond rotations happen. And so molecules actually flex and these rotations happen. Now we can actually predict sometimes which one is going to be more stable. And we're going to do that as we move along here. So if you have your kit, you can practice doing this flip-flop. So I'm going to take this up triangle here. We'll show it once more. This up triangle on my right hand. And I'm going to flip it down. And the down triangle is going to flip up. And here, if you want to draw in your notes, we can see how the up triangle goes down, the down pointing triangle goes up, and we get this second chair conformation. All of the axial became equatorial. All of the equatorial became axial. So once more here, grab the two carbons that are far away from one another. The down triangle goes up, the up triangle goes down, and all the axial and equatorial have swapped positions. So as we predicted with a show of hands a few minutes ago, the axial positions have some steric repulsion happening. If these three balls are all in up equatorial or up axial positions and down axial positions, they're really in each other's space. But if we do that flip-flop, we can see all of these indicated substituents are now in equatorial positions. So depending on what the molecule is, what the substituents are, what those different side groups are, we can compare if those, depending on chair 1 versus chair 2, with that flip-flop flexing, if it's going to be in an equatorial or in an axial position. For this particular molecule, 95% of the molecules, if you have like 1 million molecules or a mole of cyclohexanes with a methyl substituent, large majority, 95%, at any given moment, they're going to have that methyl group in the equatorial position. Maybe 5%-ish are going to have this one in an axial position. But they're going to be flexing, they're going to be going back and forth, but spending most of the time with that large group in an equatorial position. So every cyclohexane, regardless of what those side chains are, maybe there are 3 side chains, maybe there are 2 side chains. They could be in axial or equatorial positions, but every chair has a flip-flop. Every single one has 2 chair conformations. So my question for you is, which of the following molecules is shown in its most stable conformation? So we have chair 1 and chair 2. Only one of the conformations is shown for each one. Which one is shown in its most stable conformation? Chat with the person beside you and submit your answer. And if you have your model kit, you can go ahead and build them and see what happens. And 10 more seconds. And 3, 2, and 1. Okay, just over half went for C, and I'm going to agree with you on that. That means that over half of us recognized this substituent here, a carbon with a methyl group, 3 methyl groups actually, so it's very bulky. The bulkiest substituent, the biggest one on any given molecule, is in the equatorial position here. Equatorial as in contrast to an up or down axial. The largest substituent is in an equatorial position, therefore C is its most stable conformation. If we did the flip-flop, that big group would have been in an axial position, which would have a lot more steric hindrance. For teaching purposes, I have also built molecule 1. It's really handy to build these sometimes to convince ourselves that it's true. So A shows I'm indicating my methyl groups with a red ball, a down axial in the front right carbon, and an up equatorial, and then an up axial in the back. A has 2 axial and 1 equatorial. But if we hold our carbon cyclohexane like this, I'm going to take the down triangle and flip it up, the up triangle and flip it down. You can see I now have 2 methyl groups in equatorial positions, only 1 in an axial position. So the chair conformations that's not shown in A has more substituents in equatorial positions. So the one shown is not the most stable. Right now, A shows an axial, and equatorial arrangement. But if we did that flip-flop, it would become equatorial, axial. The other option, the other chair conformation, has more equatorial substituents. The one that's not drawn is the more stable. And that's what we would do for each molecule. Where's the largest substituent, axial or equatorial? Or if they're all the same, which one has more of those substituents in equatorial positions? Thumbs up if that makes sense. Awesome. Okay, let's keep moving along here. So a nice little recap we have here. We have talked about conformations. Those aren't different molecules. That's just a flip-flop. Or, if you look down a carbon-carbon bond with a Newman projection, rotating around that carbon-carbon bond. It's still the same molecule, it's just a different conformation. And we know how to do that with Newman projections and cyclohexane chair conformations. But we've also talked about constitutional isomers. That's when we have different molecules, different properties, different boiling points, melting points, whatever, and they have a different connectivity. So if you put your pencil down and try to say the molecule structure out loud, it's going to sound different. It's going to look different. Atoms are connected to different atoms. We've already looked at constitutional isomers for acyclic hydrocarbons, ones that aren't in a ring. Now we're going to look at ones that are in a ring. So constitutional isomers for cyclohexanes. So we could look at this methyl group and this methyl group and see they're both coming off of carbon 1 of this cyclohexane. So if I looked at my structure here, I could look at my cyclohexane and see I have 2 interesting groups, 2 methyl groups, coming off of the same carbon atom. So we could call it 1,1-dimethyl cyclohexane. That would be one of the names. But if we wanted to break a bond and form a new bond and attach the methyl group to the next carbon, we could make 1,2-dimethyl cyclohexane. and it has a different connectivity. The methyl group is attached to a different carbon. I could also add this ball to carbon 3 and make 1,3-dimethyl cyclohexane, or to carbon 4, a different connectivity. 1,1, 1,2, 1,3, 1,4, those are all constitutional isomers because they have different connectivities. When I go from 1,1, I know where to put this red ball. It just goes on the available prong, right? Rather than a carbon hydrogen, it's going to be carbon methyl or whatever. But when I go to carbon 2, I have two choices. Do I put it on the up one or the down one? Is it going to result in a different molecule if I do that? And it very well may. Depending on if I put it in the axial or equatorial position, it could result in a different molecule. So whether this is coming towards you or whether that methyl group is going away from you, that's going to result in a different type of molecule. So we have constitutional isomers, depending on which carbon we put those methyl groups on. But then we also have a stereoisomer option happening for some of these, because depending on if you put it on the substituent pointing this way or put it in the bonding region pointing away from you, that also makes a different molecule. This is where we get stereoisomerism in cycloalkanes. Whether I put this on the same side or opposite side, whichever one I choose, that's going to give me a different molecule. Not a different constitutional isomer, because I'm still coming off of the same carbon 2, but whether it is, and I could squish this down, if you have your cyclohexane, we know that it is in a boat or a chair conformation, but just for now, let's squish it down. This isn't how it actually exists. So you can see how it pops up right away. It doesn't want to stay that way. But if you put all the carbon atoms in the same plane for at least a moment, it's easier to see if relative to the carbon plane, the substituent is pointing up or pointing down. I'm going to make my carbon, or my interesting substituent, my red ball, point up. To add it to carbon number 2, you can see it's very quickly turning into a chair conformation. It doesn't want to stay flat because this one is eclipsed. That's why it doesn't exist like this. But cooperate for just a second. This one is above the carbon-carbon plane. So if I want this ball to be on the same side as the carbon-carbon plane, they're both up, I would put it in this position. If they're both up, then they're on the same side, which we call cis. So in chemistry, cis means the same. So they could be up, up, or without changing anything, I'm just going to look at it from a different angle, they could be down, down. In contrast, I could break that bond, form a new bond, which tells me I have an isomer, not just a different conformation, squish it down. Now I can see one of them is above the plane of the carbon atoms. One of them is below. Now they're on opposite sides. One is up, one is down. So this would be a trans isomer. That's the word we mean to mean different here, or opposite sides. So one is up, one is down. Cis and trans are stereoisomers for cyclohexanes. So we could draw it like this, even though we know it's actually in a chair conformation. We could pretend to ignore that, even though it does exist that way. But we could draw it as you see projected here. Notice that chair conformation looks flat when you're just looking on a paper like this, but remember it's still chair. If one of them is up and the other one is relatively up, we could squish it down and see they're both popping towards us. So we could draw them with both wedges coming up towards us. We could also draw them with both wedges pointing away from us. In contrast, we could put one up and one down on the trans side, and we would have a different stereoisomer. If we have the option, and changing from that towards you versus away from you makes a different molecule, that means we have a stereoisomer. I'm going to skip this question in the interest of time. We'll come back to this one later. Now, we've shown how we can go up, up, and down, down. But now let's turn this back into a chair conformation. So take your cyclohexane, bring it into a boat, both hands up, and then whichever hand you want, push one down. And then we have our beautiful chair conformation with 3 down axials and 3 up axials. When we're looking at up to down or up to down, right now I have my molecule in a cis isomer. If I look at this carbon here, I can see that my interesting substituent is up compared to the other substituent. So this would be my up axial and down equatorial. Up compared to down. If I rotate here to the next carbon, this red ball is also up relative to the other option here that's very much pointing down in an axial. So we can talk about up and up, even though one is an axial, one is an equatorial, because we're always comparing to the other substituent on that carbon atom. Or we could squish it down and see that it's above the plane of the carbons. So this methyl group is up compared to that hydrogen. This methyl group is up compared to that hydrogen. In contrast, if we break a bond and we put that methyl group in a down position, this one is now down relative to the hydrogen. This methyl group is up relative to that hydrogen. Up and down are opposites. That gives us trans. Up and up are the same side. That gives us cis. Of course, we could look at it from another way, and it could be down, down, and that would also count as cis. So we are going to start this exercise. So build your cyclohexane, and we are going to start with a 1,2 trans cyclohexane. First step, first challenge, is to build the molecule exactly as you see it in this in our slide here. So have a methyl group or a red ball pointing down on that front right carbon, and a methyl group pointing up on the back or the second carbon. In this exercise, it's quite a big exercise, we'll start it today. We're looking at 3 different constitutional isomers of cyclohexane. One, 2, 1, 3, and 1, 4, those are constitutional isomers. All the examples that we're going to do on this slide are based on the 1, 2 constitutional isomer. We're going to look at the trans option and the cis option. And if we compare those two, we're going to see these are stereoisomers. We have to break a bond and form a new bond to go from trans to cis or cis to trans. But it's built off of the same constitutional isomer. We have a methyl group. I'm going to call this carbon 1, a down axial on carbon 1, and up axial on carbon 2, versus an up equatorial on carbon 1 versus an up axial on carbon 2. Up, down tells us it's trans, up, up tells us it's cis. So we have constitutional isomers, 1, 2, 3, depending on where those carbons are added. Then we have cis-trans stereoisomers we're going to investigate. And just to keep it exciting, we also have conformations. So we can see that our 1, 2 trans molecule would look like this. So right now, hopefully you have the same molecule built. Carbon 1 has a down methyl group. Carbon 2 has an up methyl group. They're both in axial positions. One is down, one is up. This is our trans stereoisomer. But this ring can undergo flexing. It can undergo flip-flop. So now we're going to make the molecule in the top right. I'm going to take this down triangle with carbon number 1, and I'm going to flip it up. And I'm going to take the other carbons that's opposite from my hand and flip that one down. And then I'm going to hold it just like I see in my workbook. This carbon 1, this methyl group, is still down, but now it's in an equatorial position. On carbon 2, this methyl group is still up, but now it's also in an equatorial position. So let's go ahead and label these here. So I now have my methyl group on this carbon 1 in a down equatorial. I have this methyl group in an up equatorial, which means I have my hydrogens in those other positions. So then this question says, well, which one is more stable? If we have these two conformations from the same constitutional isomer, from the same stereoisomer, they're both 1,2 trans, we have the option of up-down axial or up-down equatorial. Which one is more stable? We're going to go by show of hands. Who says it is the up-down axial? Chair 1. Who says it's chair 2 when they're both in equatorial positions? And I agree, they're in that position that has more space. So this conformation of 1,2 trans is more stable. Okay, next class, bring your cyclohexane. We are going to continue this example, and we're going to continue it next class. But before we wrap up today, we have a very special presentation. I'm very excited to introduce Marietta. Come on up. Marietta come on, give her a round of applause. Awesome. So Marietta has done her degree in a chemistry-related field, and she is doing something very cool. And in chemistry class, we want to teach you chemistry, but we also want to show you how chemistry applies to future professional schools and careers. So we're going to take the next few minutes and hear from Marietta how chemistry can lead to some very exciting degree pathways. And just like all of our guest speakers, this could show up on the exam. So please join me in welcoming Marietta.